accepts, right? Okay, so I'll leave you with that to stew on. So whatever D does, it's forced to do the opposite. Whatever D does. Okay. So I need to clarify this a little bit. Concentrate on this. Okay. So D of D accepts. When does it accept? Well, when D does not accept this. So not accept. So you can put D angular. Sorry, not angular. Round brackets D round brackets angular D. So in other words, D accepts this if D does not accept this. Okay? And D rejects this, this here, if D accepts this. That's just flatly contradictory. It's just X and not X, right? You got yourself a blatant contradiction there. Okay? You follow this way. Well, I've written it out in the Sipser way, but it's not the typical Sipser. Is not so clear, but you're spelling it out this way. So D of angular bracket accepts if D of angular bracket does not accept. Okay, just flat contradiction. And there it is. You got yourself a contradiction, and then we can draw all the necessary conclusions. We've got a contradiction, just a flat logical contradiction, a bit different from the others, and therefore we have a contradiction, and therefore by using the proof by contradiction, we can go back and negate what we started with, and what we started with was that the language A suffix TM is decidable. So we negate that, and therefore A of TM is undecidable. Ta-da! Sort of mini trumpet, right? Okay, so this D, because of this contradiction, this flat logical contradiction, so D can't exist, okay, and therefore H, and if D can't exist, then H can't exist. And remember, H was the decider of A of suffix Tn. So if H can't exist, then that language, A of Tn, is not decidable, because there's no Turing machine, H cannot exist, therefore there's no Turing machine that can decide that language. Therefore, A suffix Tn is undecidable by definition. Right? Now, I hope you followed that. And then Sipser goes into a kind of, let's review the proof, right? So here's the logic again. You're using proof by contradiction. You're trying to prove that A of suffix Tm is undecidable. So you assume the opposite. Therefore, A of Tm is decidable, and therefore there's a Turing machine H that decides it. Okay. And we'll use H as a component, as a part, to build a Turing machine D. What does D do? So when it's given an input, the string, which is a description of some Turing machine M, then it will accept when M does not accept input description. Now, we've done this a bit before, but remember H accepts if M accepts this, and H rejects if M rejects this. Okay, and so he's left out a line, but yeah. Okay. All right, and then the punchline in the proof is to let M be D. So you've got D. The input string to D, instead of being this, for some arbitrary machine M, it's now angular bracket D. So the encoded information about D itself. So the input string to D is the information about itself. Right? And when you put D here, then you get a contradiction. So D will accept angular D if D does not accept angular D, and D will reject angular D if D accepts angular D. Right? That's a contradiction. So it's just nuts here. So D rejects this when D accepts this, effectively. Right? No umpteen exclamation marks. All right. Now moving on a bit. Now I've been talking about the use of diagonalization in this proof. Well, so far we haven't made any mention of diagonalization. So where does that come into the proof? 4.11. That proof, the theorem statement is the language A suffix TM is undecidable. Okay, that's theorem 4.11. Okay, so to answer this question, I'll show where diagonalization does come in. We need to have a look at a whole bunch of tables and how they behave for Turing machines H and D. Now, what are these tables? Well, they're infinite tables, and like you label each. Well, you form these tables are matrices. Okay? A table is a matrix, and the label on the left-hand side of each row is a Turing machine of all Turing machines, M1, M2, ... Okay, and the headers of the columns in this matrix, this infinite matrix, are the descriptions of the Turing machine. So angular brackets M1, and the second column would be labelled angular brackets M2. The encoding of that in string format of each Turing machine for all Turing machines. Okay, so okay, so that now the entries of the elements, if you like, of the matrix, this infinite matrix, for machine what is it, M. Well, I'm getting well into the next session, so I'll probably good moment to stop there and just go straight on.